All right, with that, let's get started talking about physical AI and robotics. There was a lot of that in Jensen's keynote yesterday, and I think maybe that piqued your interest in what's going on, so we can delve into it in a little bit more detail. This whole AI thing, the modern AI thing, started a little over 10 years ago with the invention of deep learning on our GPUs at the University of Toronto. It was AlexNet that kicked it off, first contact, where we, for the first time, were able to develop an algorithm that solved a long-standing computer science problem, one that had vexed computer scientists for many, many decades, using a brand new method of developing the algorithms. The problem I'm speaking about is image classification, being able to determine what is inside an image. We'd been trying to do that since the 1950s, and basically had given up on the problem. But when AlexNet was introduced, it showed up and smashed all records, all benchmarks in image classification, and set off this new era of AI. Now, what was special about this wasn't just that we solved that particular problem or the greater problem of computer vision, but the way we solved it was novel. Instead of having humans develop the software directly, design an algorithm directly, we took a bunch of examples of what we would like the algorithm to do, and we fed it into a supercomputer, and that supercomputer wrote the software for us. This was the fundamental change that's kicked off everything we've been talking about here at GTC for the past 12, 13 years or so, and what Jensen was talking about yesterday in the keynote. We started at first with perception AI. The first algorithms we developed were very narrow. They solved particular problems, and mostly in the area of perception, computer vision, speech recognition, audio processing, these sort of things. In this era, we had to collect data, examples, to feed into the AI factories that were very niche and specialized for the particular algorithm that you needed. Still amazing, but somewhat limited in what they could do. In around 2017, 2018, this all changed with the invention of the transformer architecture. The transformer architecture allowed us to take large amounts of unstructured, unlabeled data, essentially all the information we can find on the internet related to text, shove it through an even bigger supercomputer, and what came out of that is a neural network that encodes all of the patterns that we find in language, all of the rules of language, all of the laws of language. That gave us a new capability. It allowed us to generalize these neural networks and use them for many, many purposes, not just one specific thing. For example, you can take one of these large language models and have it take a small amount of information, a small text prompt, and have it produce a large amount of information, something like a poem. You could take that same information, the poem, and have it transfer it or restyle it into a rap. You can then take that same information, the large amount, and have it reduce it to a smaller amount of information, a summary of what's inside, or gather insights from it. So this was what was amazing in this era, the generative AI era. We can use these large models for many different purposes because fundamentally the intelligence that's encoded in there is a somewhat fundamental understanding of the basic laws of the thing. We are now currently entering the era of agentic AI. This is where we're taking this foundational technology, the generative models, and we're building systems where these generative models can act autonomously. The models we have currently act in the information space, they act in the digital space. We can have them perceive what is going on inside the internet, what's going on in your computer directly. That's their natural space. They perceive, they make some decisions, and then they can go act. They can make some API calls and do things. As a result, we can create agents that do customer service, agents that can go purchase things on your behalf, set up your itinerary for a trip, act as an assistant in your calendar, this sort of stuff. Basically, robots that do knowledge work, much like most of the people in this room who probably do knowledge work. We interface with computers and we do things inside a computer. That's what these agents can do. What we're here to talk about today is the era that is coming. And this is the physical AI era. Essentially, we're going to build upon everything we did in the past in AI, what we've been doing for the last 10 years, but bring all of that stuff into the physical world. These agents that operate autonomously inside our computer systems can now come out into the physical world if we give them bodies, if we give them a physical form that allows them to sense the world, allows them to make decisions about that, and then to act. If we can do that, that unlocks orders of magnitude more value from these agents than the current ones that we have that are limited only to our IT space. We can have them come out here working with us, helping us inside the physical world, manipulating not only ones and zeros, but manipulating atoms. So what is a physical AI? In its simplest form, we can think of it as an AI that takes as input sensor information about the world, the physical world, gathered through various sensors, things like images from cameras, along with a lot of the other traditional AI information. We can give it text and language and prompts. The model then processes all of this, and out comes tokens that represent actions, things that we would like the physical agent to do inside the world. So at its essence, you can just think of physical AI as a brain of a robot that takes input, just like we do, from our sensors, from our eyes and ears and touch sensors from our skin. We do a bunch of processing, and ultimately we send out control signals to actuate our muscles and act inside this world to manipulate things in here. The three classes of robots that we are talking about, the three really important ones, are robots, like the things we normally would think of if you say the word robot, humanoids. You know, we have all the sci-fi, R2-D2, C-3PO, and so on and so forth. So these types of robots are the ones that are coming online, and it's generally what we think. But essentially, any agent that has a physical embodiment inside the world and can do all three of those things, perceive, plan, and decide, and act, are robots. That includes things like spaces, physical spaces, such as factories and warehouses where you have sensors like cameras, and you can have actuators for things happening inside it, or other robots within those spaces that are controlled by them, or autonomous vehicles. A robot is a type of robot. The car is the body, and the AI that's driving it is essentially the equivalent of a driver who is perceiving the world and acting. In order for the United States to be successful in its mission, to be successful in what Jensen was talking about yesterday, in terms of reindustrializing America, bringing back all of this manufacturing, so we can not only continue producing all of the things we need today, but produce all of the things that we need in the ensuing years, we need to have physical AI and we need robotics. As we speak today, we have a huge labor shortage. There are 500,000 unfilled manufacturing jobs in the US today. And this is only going to get worse. We estimate that there's going to be 4 million unfilled jobs by 2033. These jobs are jobs that largely the younger generation doesn't want to do. And given the demographic challenges happening everywhere in the world, we're going to have this problem everywhere where we don't have enough labor to continue producing at the rate we produce today because the number of people that can do those jobs just don't exist. Instead, what we want to do is have our humans be the directors of the robots doing the dull, dirty, and dangerous work. In order to build a robot, in order to build the brain of a robot, the physical AI, and to deploy these robots, you need 3 computers. You need a computer that is actually in the robot, that is powering it, that runs the brain. That's NVIDIA Jetson, our Jetson and our drive computers and our IGX computers. Thor is the latest one that we announced. That's a very important computer, but it's not the only one. Equally important, if not more important, is the computer that produces the brain that is actually deployed onto that computer. That's our AI factories. This is largely what we've been talking about here at GTC, and what most of you know NVIDIA for. I think as of today, we're probably a $5 trillion company. I haven't checked the stock price, but it's because of that particular computer that we are there. But there's a third computer most people don't attribute to robotics, but is essential for us to create this, and it's the simulation computer, or what Jensen yesterday called the Omniverse computer. This is the computer that takes the laws of physics, where we take the rules of the world, and we reconstruct the physical world inside a virtual world running on this special computer to generate all of the data we feed into the AI factory that then produces the brain that we then deploy onto the robot computer. You also need this simulation computer for a second purpose. Not only do you need it to generate the data that produces the brain, but you also need this computer in order to test that brain before you deploy it. We cannot build physical AI that has a high degree of failure. Even a 1% chance of failure in the real world can have catastrophic consequences. You can imagine what those could be, operating heavy machinery in a factory or driving in our streets. So we want to drive them for millions and billions of miles and run them for millions and billions of hours in diverse conditions well before we actually put them in the physical world. And we do that on this computer in the virtual world. To do that, we build layers and layers of software to help our application developers and our solutions providers build simulations of the real world. We call this, for the simulation computer, we call it NVIDIA Omniverse. Omniverse is a collection of libraries and APIs. Developers take our libraries and APIs, choose which ones are appropriate for their particular application and simulation, and they build new simulators, applications, and tools to build digital twins and simulations of the thing at hand. We make these available as libraries, and we also provide blueprints, which are essentially examples of how you can integrate all of our technologies into a working solution that you can modify. So with that, I'm going to play a little video that shows you a collection of examples of the types of things you can do with our Omniverse technologies. These simulations that we build to build these physical AIs are used for many different purposes at many different scales. They work at product scales, at facility scales like factories, AI factories themselves. We are simulating all the way up to cities and even the Earth. Here's an example of how you can build a simulation, a digital twin, of a product and do simulation well before you deploy this thing into the real world. In this example, we have a fluid dynamics simulation that's been accelerated by NVIDIA's computers to, in combination with classical algorithms that we've made data parallel through our CUDA-X libraries, as well as new algorithms that are AI-based that approximate the same physics solvers to make them real-time, combined with our Omniverse libraries to make a tool that allows an engineer, a designer of an airplane, to explore the parameter space of the wings they might build. We also build digital twins of factories. We talk about two types of factories. There's the kinds of factories most people think about, the factories that build physical products. And now there's a new kind of factories that produce intelligence, AI factories. Yesterday, we announced an amazing new product, a new tool with Siemens. Siemens is developing Digital Twin Builder, which is a holistic, comprehensive digital twin assembly tool for factories that integrates all of the various tools and technologies they have in their suite, along with many of our Omniverse technologies through our libraries into one product that lets you build a digital twin of factories. Once you have these digital twins of the factories, there are many things you can do with it. They are very general. It's a platform in and of itself. You can use these digital twins to do things like layout and planning. You can simulate your processes and optimize them. You can use it for operations to monitor resources and essentially create a facsimile of the real thing in real time, but in the virtual world, so that anyone anywhere in the world can go inspect it without having to physically go there. You can use it to generate enormous amounts of data in order to train new AIs, like AIs to do industrial inspection or to train your robots. Here's some examples, many examples, but not a comprehensive list of all of them, of various uses of Omniverse in industry. We have BMW, who has been using it for years to help design their factories. The Kion Group is using it to design, build, and operate their warehouses. Mercedes-Benz as well for their factories. Scheffler, who is a manufacturer in Germany, a very important one, tier one, that provides parts for automotive and robotics. They are also doing the same thing with digital twins of their factories. Quanta, one example of many of our contract manufacturers who are using Omniverse to build the factories that build our computers that go into our AI factories that we then use to build AIs that go back into the robots that are in their factories. TSMC, building digital twins of their fabs. They have very unique challenges with their multi-floor tooling that has complex piping and routing. They use Omniverse to help optimize and design that. We announced yesterday a new blueprint built on Omniverse for building and operating AI factories, optimizing them. It's called the NVIDIA Omniverse DSX Blueprint. This blueprint contains, it's essentially a reference example of how you can build a full digital twin of an AI factory to help accelerate you building and deploying it and optimizing it, which has even small percentage optimizations in efficiency can have repercussions that are in the billions of dollars in operating it. This is built using various tools. You can see all the different partners that are involved in this blueprint, combined with our Omniverse technologies. And here's an example of what you can do with this blueprint. We have a digital twin of one of our AI factories where we can run a simulation in real time of an actual workload running, a computing workload running in this AI factory, and see in a physically accurate simulation what is the heat generated from the compute trays inside this AI factory and how the heat transfers throughout the whole system. Now, in order to build physical AI, just like any other AI, we need gobs and gobs of data. The data that you provide has to be just the right data as well. It's not enough to have large amounts of data. You also have to have a diverse set of data and data that's very relevant to the particular skills and tasks you want this AI to learn. In the information space, in the space of language, for things like LLMs and chatbots, we were lucky because we have petabytes and petabytes of information just sitting there on the internet that we could go mine and extract, just like a fossil resource. We have fossil data that we could use to do that. For physical AI, we're not so lucky. We don't have any of the data necessary for us to go build the brains of robots just sitting there on the internet. We have to go capture this somehow. In order to do that, we either have to take it from the real world by placing expensive sensors and spending all of the time and expense and potentially risking people and our materials physically in the process, or we have to figure out how to take the physical world represented inside a computer as a simulation and use that as a renewable source of physical data to generate all of the data necessary for this. And so in order to do this, we employ many technologies. The actual physical AIs we are producing with the first simulations that we build on classical simulators, we can also leverage that physical AI itself to help us with future simulations to produce even more and more data. We've started a virtuous cycle where we use classical simulation to create physical AI that then feeds back into our simulators, becomes part of the simulator, to create even more data, to create better physical AI, and so on and so forth. To do this, we are seeding the industry, seeding the world with our technology and providing it for free and in an open way. We provide open models. The two big families of models we have for physical AI are Cosmos, which is a world foundation model, and Groot, which is essentially a physical AI model that could be the core of a robot brain. We provide the data sets that we use to train these models in an open way and freely. We provide free simulation frameworks, Isaac Sim and Isaac Lab for robotic simulation, and pipelines and tools for synthetic data generation so that everyone can build on this, because this problem is much bigger than NVIDIA. The problem of creating physical AI and robotics is much bigger than any company. We all have to participate in this together if we're going to make it happen. And so we firmly believe that the only way to do this is to take the resources and the capabilities NVIDIA has and make them freely and openly available to everyone else to go build on top of. In order to build, to create all of this data, we need to construct these virtual worlds to construct these simulations and the content that goes into them with some method. And traditionally, this has been very, very difficult. It takes highly skilled niche expertise to build simulations and simulatable virtual worlds, 3D worlds. Fortunately, with new technologies that are arriving every day with AI, we now have a path to constructing these worlds without having to have all of that expertise. There are three primary ways we can leverage AI in order to help us to build these data sets. The first is reconstructing virtual worlds from the actual physical world by capturing data from the physical world and transforming it into a form that we can simulate. We can also generate new worlds or new actions inside those worlds using AI. And we can also use these same AIs to take data that we are generating in simulation and annotate it for us to understand what's inside that, so that when we do use that data and feed it back into an AI factory to generate a new brain, those annotations can give critical information to the AI so that it can be smarter. Here is an example of some of our latest technology to capture the real world through sensors, through cameras and images, reconstructed through our Omniverse NuRec libraries into a form that could be ingested into Omniverse for simulation. And we can combine it with more traditional forms of digital twins that come from CAD and other appropriate representations to quickly reconstruct a world that you can use for your purposes. We can also combine classical simulation with AI to augment it in order to multiply the amount of data we generate, diverse sets of data for training. So on the left, you can see a simulation that's done in Omniverse using our more classic accelerated physics solvers and rendering that isn't using any sophisticated material models for the visual aspects of it. But from that one simulation, we can feed it through NVIDIA Cosmos, our world foundation model, and generate an infinite number of variants with different backgrounds and lightings and conditions. So we can go from one simulation run and one point of data to thousands or even millions of points of data that could then be fed into another AI. And in this example, we use Cosmos Predict, which allows us to take one image on what you see on the left side, along with some text that describes a scenario, and it, with the knowledge that it has about the physical world, can generate all of the subsequent frames, doing essentially a physics simulation completely generated by AI on the right side. From that, we can label the data, figure out the trajectories of what that hand would be inside this AI-generated virtual world, and take that data and feed it into our physical AI training systems. So here's a video that kind of shows how it all comes together.
Generalist robots must reason, plan, and act across many environments and tasks when given instructions. To learn new tasks, developers train robot models on real-world data. But human demonstrations are costly to capture. Groot Dreams is a blueprint for synthetic data generation and neural simulation, built on NVIDIA Cosmos. Using a single image and natural language, developers generate synthetic world states, or dreams. These passive dreams can be generated at scale. But prompting with natural language has its limits. For more complex tasks, developers use teleoperation to interactively control a robot in its dreams, generating lucid dreams. The dreams are used to post-train a reasoning vision language action model, like GR00T models. The trained model is evaluated in Isaac Lab, a conventional simulator providing physics feedback. After passing evaluation, it's deployed to the robot. Generalist robotics is within reach, accelerated by NVIDIA Isaac GR00T.
So very quickly, these are the two classes of physical AI models and frameworks that we are providing. We have a family of models and data sets and libraries. You can take a quick picture of that. I won't go through each one of them because we're running out of time. And I'm going to show you a few examples of applications of some of our technologies here in the real world. Here we have one of our amazing partners, Diligent Robotics, which is building a robot for hospitals, delivery within hospitals. They use all three of our computers. The robot computer is inside the actual robot. They use our simulation computer and Omniverse with Isaac Lab and Isaac Sim to build the brain of the robot and to test it. And of course, they also use our AI computer to generate the models that are the foundation of the brain of that robot. And then there's Figure AI, same thing. All three of our computers are used in building the Figure robots. There's been a lot of really cool examples they've put out recently of some of the breakthroughs they're doing with their robots. And we saw a lot of the cool stuff Brett was talking about at the pregame show yesterday, all built on Jetson Thor. Johnson & Johnson is building surgical robots and robots for the medical space, for the operating room. These are both the robots that do surgery. In this particular case, they're building one that can operate on kidneys and do surgery in kidneys, but also help with the operating theater, where the operating room itself is robotic. It has eyes and sensors that can watch everything that's going on in there and guide the surgical robots. Kimberly, I believe, talked about this in her keynote yesterday. I urge you to go take a look at that. And of course, there's the robotaxi robots that all of us are aware of now. We're starting to see them show up in cities around the US and in the world. And very quickly, we're going to see them spread everywhere. I believe within the next year or so, almost everybody will have experience with them in their city or near their cities. Then there's some things we don't normally think of as robots that really are robots. Yesterday, Jensen announced what we are doing with Nokia for 6G to make the US and America the leader in this technology space. It's really important. You can think of these radio towers as a robot as well. They do the three things I spoke about earlier. They perceive, they sense radio signals, and these new generations of technology require a lot of intelligence in order to optimize the spectrum. We have technologies like beamforming that require a lot of computation and processing to make decisions on how to actually participate in that spectrum. And then you actuate by sending radio signals out, and there's that same robotic loop happening there. With the new generation of towers we're building, they're all going to be AI enabled with our special AI computers designed for this. And we build digital twins of cities that can simulate the radio spectrum And we can use that to optimize the placements of these towers and the design of the algorithms and the parameters for operating these towers as well to save on energy and maximize our bandwidth. We also have digital twins of cities that we use for many various different purposes. I urge you to take a look at our Smart City AI Blueprint. We have built it with many of our partners here, too many to list. And we also have a blueprint for doing Earth-scale digital twins for weather simulation. With that, I'd like to give a shout out to many of our partners inside this robotics space. Everything we do is insufficient in order to make this all happen. The only way our technology actually gets into the hands of people who need it is through our partners. We are hyper-focused on building computers, on building computing technology. By itself, our computers can't do anything useful. It requires developers to go build on top of our computers, to go build on top of all of our technology, to take that to market. And so we participate in every aspect of robotics in the industrial space, but we ourselves don't actually do any of those things. We build the computers that power all of them. So here you can see many of our partners, the robot makers, the robot brain makers, the sensor makers, the application developers for the design of all of the robotic systems with CAD and reality capture and so on. And with that, I'm going to play a short video of our favorite robot. You might have seen it yesterday, but it's worth taking a look again. This is work we're doing with Disney Research on a new physics engine called Newton. It's open source. I urge you to take a look at that. And with that, please come join us in our community. We have a very active community on Discord. This is the QR code for Discord. Go check it out and go find some friends there who can help you with getting on board with all of our technologies, and come join us in building the future. Thank you.